Hi guys, in today's video we're going to take a look at Hess's law, enthalpy cycles using the enthalpy change of combustion and the enthalpy change of formation, an exam style question, and finally a summary.
Hess's law was proposed by Germain Hess, a chemist and a doctor. Hess's law states that the enthalpy change of a reaction is independent of the route that is taken. So if we have this reaction here, where A plus B is going to form C, if we call the reaction that forms A plus B forming C delta H1, then we have delta H2, and this is the reaction of A plus B to form D. If we have delta H3 as the formation of C from D, this arrow here, delta H3. According to Hess's law, delta H1 is equal to delta H2 plus delta H3. So whether we take a direct route from A plus B to C, or a route that's a bit more convoluted from A plus B to D and from D to C, the enthalpy change of the reaction will be the same. So this triangle that we have here is what we call an enthalpy cycle. Let's take a closer look at enthalpy cycles now so we can see how to construct them.
So let's take a look together at enthalpy cycles. Well, the enthalpy change of a reaction cannot always be directly measured, so we can use enthalpy cycles to help us indirectly calculate an enthalpy change. So what is an enthalpy cycle? Well, an enthalpy cycle is a pictorial representation showing the alternative route of reaction between our reactants and our products. So you can see we have our reactants and our reaction A forming our products. We can instead have an intermediate, and this arrow B shows the conversion of our reactants to our intermediate, whilst the arrow C shows the conversion of our intermediate to our products. And overall we can see that A is equal to B plus C. Whether we go this way or this way, we are still converting our reactants to our products. As we can see, our enthalpy cycles are triangular. In each corner, there should be the same number of each atom. As well as energy, matter is also conserved. So we'll have the same number of each atom in our reactants, our intermediates, and our products. As we can see, the sides of our triangle are
Arrows, and they show the direction of the reaction. So let's have a look at some examples of some enthalpy cycles to understand what exactly is going on. We're going to start by looking at enthalpy cycles that utilise the enthalpy change of combustion. We can use these enthalpy changes of combustion to find the enthalpy change of the reaction. And the reaction we're going to take a look at is the formation of benzene from carbon and hydrogen. Well, carbon and hydrogen can be combusted to form carbon dioxide and water. Now, whilst the reactants can be combusted to form carbon dioxide and water, so can our product, benzene. It too forms carbon dioxide and water when combusted. So if we were to construct an enthalpy cycle, it would look something like this. We have our reaction at the top with our reactants, carbon and hydrogen, forming our product, benzene. Now you can see that down below we have the product of combustion, carbon dioxide and water. And what we see is that the enthalpy change is equal to A minus B. The reason we're subtracting B rather than adding B to A is that in combusting benzene, we're moving from benzene over here to the product of combustion down here. However, the route we want to take is from reactants to the combustion products to benzene. So you can see where the value of B is subtracted. So let's go ahead and calculate values for A and B to find a value for the enthalpy change of this reaction. Well, in order to calculate A, we can use these values here of the enthalpy change of combustion. So we have 6 times the enthalpy change of combustion of carbon, which is minus 394, to give us minus 2,364 kilojoules per mole. Then we have 3 times the enthalpy change of combustion of hydrogen, which is minus 286, to give us minus 858 kilojoules per mole. Now to calculate B. B is simply minus 3,267. So we can fill that in here, minus 3,267 kilojoules per mole. And it's a really good idea to break down your calculations like this, making it clear what you're calculating in each step, because when it comes to an exam style setting, it'll be that much easier for the examiner and for you to check through and mark your work. So now I've calculated A and B, we can substitute these values into our equation that delta H is equal to A minus B. So delta H is equal to A minus B. So that's minus 2,364 minus 858, that's our term for A, minus 3,267, that's our term for B, to give us a total enthalpy change of plus 45 kilojoules per mole. So now I've had a look at enthalpy cycles using the enthalpy change of combustion. Let's have a look at those that use the enthalpy change of formation in order to find the enthalpy change of the reaction. We're going to look at the reaction forming nitrogen dioxide by reacting nitrogen monoxide with oxygen. Now, nitrogen monoxide and oxygen can both be made from nitrogen and oxygen, as can nitrogen dioxide, our product. So our enthalpy cycle will look something like this. We have our reactants, nitrogen monoxide and oxygen, forming nitrogen dioxide. And down below, we have the constituent elements from which they're formed. Remembering that the enthalpy change of formation is the energy change when 1 mole of a substance is made from its constituent elements under standard conditions. So we have our nitrogen and our oxygen. Now, if we have a look at the route we're going to take, we're going to take a route that goes in the negative direction of A and the positive direction of B, meaning that delta H will be equal to B minus A, where A is the enthalpy change of formation of 2 moles of nitrogen monoxide and oxygen, and B is the enthalpy change of formation of 2 moles of nitrogen dioxide. So let's take a look at how we can calculate values for A and for B. Well, let's start by looking at A. We have 2 moles of nitrogen monoxide being formed, so that'll be 2 times 90, giving us 180 kilojoules per mole. Now, the enthalpy change of formation of an element will be 0, as we would just be forming an element from the element. If we look at the enthalpy change of formation of nitrogen dioxide, that's going to be 2 times 33, to give us a total of 66 kilojoules per mole. So delta H will therefore be B, which is plus 66, minus 180, giving us an enthalpy change of a reaction of minus 114 kilojoules per mole.
So let's take a look together at an example of an enthalpy cycle using the enthalpy change of formation. Well, we can use the enthalpy changes of formation to find the enthalpy change of reaction. We're going to look at the reaction of nitrogen monoxide and oxygen gas to form nitrogen dioxide. Now, both nitrogen monoxide and oxygen, our reagents, can be made from nitrogen and oxygen. Nitrogen dioxide, our product, can also be formed from nitrogen and oxygen, the same elements. We can see we have constructed this enthalpy cycle here. We have our reagents and our products, and then we have our intermediate, which in this case is the elements that our reagents and products are made from. In order to calculate delta H, the enthalpy change of reaction, we're going to want to convert our reagents into our intermediates, and then our intermediate into our product. So we can see we're going to need the negative value of A and the positive value of B. And that's why we can then go on to say that delta H is equal to B minus A. So using this and the values that we're given as the enthalpy change of formation, we can go ahead and work out a value for A and a value for B, and then calculate a value for the enthalpy change of this reaction. If we start by looking at A, we can see that A is the enthalpy change of formation of nitrogen monoxide and of oxygen. If we start by looking at nitrogen monoxide, we can see that the enthalpy change of formation of 1 mole of nitrogen monoxide is 90. We need to multiply by 2 as we have 2. So we have 2 times 90. The enthalpy change of oxygen is going to be 0, as we're converting elemental oxygen into elemental oxygen, and no energy is required to change this. So we have a total of plus 180 kilojoules per mole. Now to look at B. B, we can see, represents the enthalpy change of formation of nitrogen dioxide. The enthalpy change of formation of 1 mole is given as plus 33. We have 2, so we need to multiply by 2. 2 times 33 gives us plus 66 kilojoules per mole. Now we have a value for B and a value for A. We can go ahead and calculate a value for delta H, the enthalpy change of this reaction. We can see that the enthalpy change of this reaction is the enthalpy change of formation of nitrogen dioxide minus the sum of the enthalpy change of formation of both nitrogen monoxide and oxygen. So delta H will be equal to B, which is 66, minus A, 180.
The first question asks us to define the standard enthalpy of formation. Now we know the standard enthalpy formation to be the energy change or enthalpy change when 1 mole of a product is formed from its constituent elements in their standard state under standard conditions. So that's quite simple. Let's see how we'll answer this question. The enthalpy change when 1 mole of a substance is formed from its constituent elements in their standard states under standard conditions. A nice and easy definition to get us 1 mark. So let's move on to question 2. The structure of glucose, a hugely important molecule, is shown below. Glucose is used throughout the body in many important chemical reactions, and we're given the structure of glucose here. Glucose can be combusted to form water and carbon dioxide according to the equation below. We have 1 molecule of glucose reacting with 6 molecules of oxygen to form 6 molecules of carbon dioxide and 6 molecules of water. Using the relevant standard enthalpies of formation, calculate the standard enthalpy change of the combustion for glucose. So, we're given the standard enthalpies of formation for glucose, carbon dioxide and water, and we can use this reaction here to construct an enthalpy cycle. So let's go ahead and rewrite the equation for the combustion of glucose. There we go. And as we're using the enthalpies of formation, we can go ahead and draw the constituent elements down below. Now I can fill in my arrows for the enthalpies of combustion, and I can label the top arrow delta H1, this arrow delta H2, and this arrow delta H3. You can use A, B and C or whatever works for you, but for this equation I'm going to use delta H1, delta H2 and delta H3. So we can see that delta H1 will be equal to minus delta H2 plus delta H3, as the reaction path that we want to take is from glucose and oxygen to the constituent elements to our carbon dioxide and water, our products. So let's go ahead and work out a value for delta H2 and delta H3 so we can calculate delta H1. So looking at delta H2 first of all. Delta H2, as we can see, is the enthalpy formation of our glucose and our oxygen. Remembering that as oxygen is an element, it will have a standard enthalpy formation of 0 kilojoules per mole. So looking at our table, we can see that glucose has a standard enthalpy formation of minus 1,250 kilojoules per mole. So we can fill that in right here. Now for delta H3. Delta H3 is a standard enthalpy formation of 6 moles of carbon dioxide and 6 moles of water. So that'll be 6 times, looking at our table, the standard enthalpy of formation of carbon dioxide is minus 394. So 6 times minus 394 to give us minus 2,364 kilojoules per mole. And 6 times the enthalpy formation of our water, which as given by our table is minus 286 kilojoules per mole. So that's minus 286 kilojoules minus 1,716 kilojoules per mole. To work out the total for delta H3, that would be minus 2,364 minus 1,716 to give us a total of minus 4,080 kilojoules per mole. So now I can go ahead and work out delta H1, as we know that delta H1 is equal to minus delta H2 plus delta H3. So that's minus 1,250 plus minus 4,080 to give us a total of minus 2,830 kilojoules per mole. So for our calculation, we receive 3 marks. Where do these 3 marks come from? The first comes from correctly identifying a value for our delta H2, the enthalpy of formation of our reactants. The second for calculating a value of the enthalpy of formation of our products. And the third for an overall correct answer. So let's go ahead and move on to the final part of our exam style question. The experimentally determined values for the enthalpy of combustion does not always agree with the values in the data booklet. Suggest 2 reasons why. Here we're being asked to suggest 2 reasons. This may require us to think outside the box to give some possible reasons why the experimentally determined values are not always accurate. We know these errors and assumptions can come from things such as incomplete combustion occurring, non-standard conditions being used, or heat being released to the surroundings during the experiment. So let's suggest 2 reasons why. So I've answered by saying that this could be because non-standard conditions were used or incomplete combustion of the glucose may have occurred. And we get 1 mark for each of our suggestions.
So let's go ahead and take a look at question 3. Rockets use highly exothermic reactions to propel them. One reaction that is often used is the reaction of N2O4 dinitrogen tetroxide with methyl hydrazine, and we've got the formula for that here, CH3NH&H2. We're given the equation to show that, and we can see that our dinitrogen tetroxide and methyl hydrazine are reacting to form carbon dioxide, water, and nitrogen gas. Using the enthalpy changes of formation, which were given in this table, calculate the enthalpy change for this reaction. So the first thing I'm going to do is go ahead and rewrite our equation so we can form our enthalpy change diagram. So we can write in everything we know. So simply rewriting the equation we were given above. And now, as we know that we do when we calculate enthalpy change of formation, I'm going to write those pure elements below. So we have 4 carbon, 5 nitrogen, 12 hydrogen, and 10 oxygen, where our nitrogen, hydrogen, and oxygen are diatomic, because that's how they exist in their standard states. So now I'm going to go ahead and draw in the arrows. So we're showing the formation of that and the formation of that. We can go ahead and label our arrows now. So we've got delta H1, which is what we're trying to calculate, the enthalpy change of the reaction, delta H2, and delta H3. So you can see that we're going to want to calculate delta H1, which will require us to do this and this, meaning we'll need the negative of delta H2 and the positive of delta H3. So delta H1 is equal to negative delta H2 plus delta H3. Now to calculate a value for delta H2. We can see that we're forming 4 molecules of our methyl hydrazine, and in the table we're told that the enthalpy change of formation for that is plus 54 kilojoules per mole. So that's 4 times plus 54. We're also forming 5 molecules of dinitrogen tetroxide, and the enthalpy change of formation is minus 20. So that's 5 times minus 20, giving us a total of plus 116 kilojoules per mole. Now to work out delta H3. We can see that the enthalpy change of formation of our carbon dioxide is minus 394. So we've got 4 lots of that, so it's minus 394 times 4. We add to that the enthalpy change of formation of our water molecules. We have 12 of those, and the enthalpy change of formation is minus 242. So that's 12 times minus 242. Now you can see that we have 9 molecules of nitrogen. Now we're forming diatomic nitrogen from diatomic nitrogen, so there's no change going on here, and there's no enthalpy change of formation for that. So our delta H3 has a total of minus 4,480. Substituting those values back into our equation here, we can see that we need the negative value of delta H2, so minus 116, plus delta H3, so plus minus 4,480, giving us a total value of minus 4,596. So our answer is minus 4,596 kilojoules per mole. This calculation question is a little bit long-winded, but if we break it down like we've done, working out what we need to look at and whether we've got the positive value of delta H2 or the negative, and the same for delta H3, and then breaking down the different parts of our equation and then bringing it all together in the final steps, we can really work through it quite methodically. 1 mark is awarded for the correct enthalpy formation of our reactants, so in this case delta H1. The same for our products, which in this case is delta H2, and the same for our products, which in this case is delta H3, and the correct overall answer gets us our third and final mark. Moving on to question 4. Glucose can be formed according to the equation below. I've got 6 carbon, 6 hydrogen and 3 oxygen molecules making 1 molecule of glucose, C6H12O6. The enthalpy change of formation of glucose cannot be determined directly. We're asked in part 1 to suggest a reason why this is the case. So this could be for many reasons. It might be because the rate is too slow, and that would make it difficult for us to determine the enthalpy change of formation directly. This would get us the 1 mark. We could make some alternative suggestions, including that the activation energy is too high, as that would also make it difficult. And looking at our reagents, it's plausible to suggest that rather than forming our glucose, we could form carbon dioxide and water instead, making it difficult to actually determine the enthalpy of this reaction. Any of these suggestions would get us a mark. For a question like suggest, it's important you think a little bit outside the box, but still apply the principles of chemistry that you know to make sure it's a plausible suggestion. Moving on to part B. This table shows some enthalpy changes of combustion, and we're given them here. Use these enthalpy changes of combustion to calculate the enthalpy change of formation for solid glucose. So, where do we start? Firstly, let's go ahead and write in the equation that we know, the formation of glucose, which we were given above. Now if we write in the combustion products, we can see that both our reactants and our products will combust to form carbon dioxide and water. Balancing that, we've got 6 carbon dioxide and 6 water molecules. Now if I go ahead and draw in my arrows, we're looking at enthalpy change of combustion, so the arrows are going to go in that direction. Now if I go ahead and label it, we've got delta H1, which is what we want to calculate, delta H2, the enthalpy change of combustion of all of our reactants, and delta H3. Drawing in the direction we want to go, we want to calculate this. We've got the positive value of delta H2 and the negative value of delta H3. So delta H1 is equal to delta H2 minus delta H3. Now to calculate delta H2 initially. So for delta H2 is the sum of the enthalpy change of combustion of all of our reagents. Now if you look in our table, we're given the enthalpy change of combustion for carbon and hydrogen, but not for oxygen, because combusting in oxygen is really just forming more oxygen. So there's no enthalpy change of combustion for our oxygen. We have 6 carbons, so that's 6 times minus 394. We've got 6 hydrogen molecules, so that's 6 times minus 286, to give us a total of minus 4,080 kilojoules per mole. Now to look at delta H3. We're simply combusting our molecule of glucose here, and in the table, the enthalpy change of combustion has given us minus 2,801. So 1 times minus 2,801 is equal to minus 2,801. Now, according to our equation here, delta H1 is equal to delta H2 minus delta H3. So that's minus 4,080 minus 2,801, which is equal to minus 1,279 kilojoules per mole. Again, we have one of those long-winded calculation questions. 1 mark is awarded for correctly constructing this diagram here, showing our reactants, our product, and the correct combustion products. 2nd mark is awarded for calculating delta H2 correctly, the sum of the enthalpies of combustion of our reactants. The 3rd for delta H3, and the 4th for a correct overall answer.
Hey guys, I hope you're enjoying the video. If you're looking for an amazing A-level chemistry resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level chemistry a walk in the park.